algebra, and we're going to do serious experiments. None of this open to chapter 7 and do all the odd problem sets. We're going to be doing genuine physics. And that's one of the things I thought I'd do right now. Before even turning that on, one of the things that we did about 3 weeks ago in my class, this is through the lens, and one of the things we used the lens for was to measure the speed of light. My students in El Cerrito, and with my help, of course, and the help of a very beat-up oscilloscope, measured the speed of light. We were off by 25%. How many 8th graders do you know of that have measured the speed of light? In addition to that, we've measured the speed of sound. I'd love to measure the speed of light here. I was all set to do it, and I was thinking, oh man, I'm just going to impose upon the powers that be and measure the speed of light. And I'm all set to do it. But then it turns out that to set up here, you have like 10 minutes to set up, and there's no time to do it. So next time, maybe, I'll measure the speed of light. But meanwhile, let's measure the speed of sound. Well, the obvious way to measure the speed of sound is to bounce sound off something and look at the echo. But probably, one of my students, Ariel Karat, said, could we measure the speed of light using the wave equation? And all of you know the wave equation is the frequency times the wavelength of any wave is a constant. When the frequency goes up, the wavelength comes down. Wavelength goes up, frequency goes down. So if we have a wave here, that's what's interesting. As the pitch goes up, things get closer. Pitch goes down, things stretch out. Right? This is simple physics. All of you know this from 8th grade, remember? What they didn't tell you in physics, in 8th grade physics, but they should have, and I wish they had, was that if you multiply the frequency times the wavelength of sound or light, you get a constant, and that constant is the speed of sound. So in order to measure the speed of sound, all I've got to do is know its frequency. Well, that's easy. I've got a frequency counter right here. Let me set it up to around A above A above A. There's an A, more or less. Now, so I know the frequency. It's 1.76 kilohertz. Let me measure its wavelength. All I need now is to flip on another beam, and the bottom beam is me talking, right? So anytime I talk, you can see it on the screen. Yeah. I'll put it over here, and as I move this away from the source, you'll notice the spiral, the slinky moves. We're going through different nodes of the wave coming out this way. Those of you who are physicists, I hear you rolling your eyes, but bear with me. To measure the wavelength, all I need to do is measure the distance from here, one full wave over to here. From here to here is the wavelength of sound. So I'll put a measuring tape here, move it back over to here. I've moved the microphone 20 centimeters, 0.2 meters from here, back to here. 20 centimeters? Okay, let's go back to Mr. Elmo. And we'll say the frequency is 1.76 kilohertz, or 1760. The wavelength was 0.2 meters. Let's figure out what this is. 1.76 times 0.2 over here is 352 meters per second. If you look it up in the book, yeah, it's really 343. But here, with kludgy material and lousy drink, we've been able to measure the speed of light with the speed of sound to not bad, pretty good. Thank you very much.